Hi everybody, welcome back. Today we're going to continue our discussion about oblique shocks and then proceed towards talking about another structure that's common to external flows, which is expansion waves and Prandtl-Meyer expansion fans. So last time we discussed oblique shocks in detail, and the diagram you want to keep in mind really is that you have some V1 coming in. This is the oblique shock at a shock angle theta, and then you have some parallel component as well as a perpendicular component, so V perp 1. And then you have V parallel. V parallel doesn't change across the shock. And then on the other side of the shock, you have a smaller V perp 2. That's what's changing as you pass through the shock. And then V parallel is the same as before. And your overall V2 looks like that. So V parallel, same as before, V perp 2. Okay, and that's sort of the basic picture for an oblique shock. We talked about how oblique shocks are often occurring to satisfy some sort of change in direction, boundary conditions. So you have some sort of M1 coming in this way, and then a shock, and then M2 going parallel to the wall beyond that shock. And how when we have a really high required change in direction, then where this deflection angle is greater than delta max for a given incoming Mach number, and 1, that in that case you have a detached shock and then subsonic flow downstream of that detached shock. Okay, so one example of how you might use this structure in particular is the inlets to jets, and hopefully I'll have the chance to show you some detailed video about that kind of shows these shock structures. But one thing that you can't have on an inlet of a supersonic jet, say something like the SR-71, is your jet inlet geometry might look something like this, where you have an oblique shock at the leading edge, and then there's another change in direction that causes a compression, and therefore another oblique shock will form. And then finally at the inlet is where you get that sort of normal shock, right? And so you have your initial flow coming in this way, then there's a change in direction here, another change in direction here, and then subsonic into the engine that way. Okay, so essentially you're using several steps of deflection to reduce the strength of the normal shock at the inlet. Okay, so in other words, this sort of situation that we've drawn here has less losses than the case where you say have an inlet just straight from the incoming flow, and then just a normal shock that's occurring at the entrance of the inlet. Okay. Okay, so that's one way that you can use these oblique shock structures, that you often actually see them when you analyze these propulsion systems in detail. All right, so let's talk about pressure equilibrium now. So we talked about how equilibrium. We talked about how the oblique shocks are happening to satisfy a change of direction boundary condition, but they can also occur to satisfy a pressure boundary condition. So let's imagine we have some sort of de Laval nozzle that's looks like this. Okay, so this is the wall. All right, and then let's say that at the exit we have some sort of exiting Mach number of m1. Okay, and then let's draw the center line of this guy like this. You'll see when I'm drawing the center line in just a moment. So let's talk about this. We talked about in lecture 6, so a couple of lectures ago, that at the second critical we get a normal shock at the exit, right? So, and the reason why that normal shock was occurring was so that the receiver back pressure or receiver atmospheric pressure would be the same as the pressure after the exit of the nozzle. So it was that normal shock was occurring to meet that boundary condition. So recall that normal shock at exit at the second critical occurs to meet the P B or P receiver boundary condition. Okay, so the shock's causing this abrupt increase in pressure to meet that boundary condition. So the question now is like, what happens if PB is reduced further beyond the second critical operating condition, right? And so right now you're in between the second and third critical points. So at the third critical, remember there's no shocks. It's isentropic flow throughout all the way to the exit and through the exit. And so what happens in that case is you get oblique shocks because you don't need as strong of a pressure drop as you would get with a normal shock. But you still need an extra pressure drop to meet that boundary condition, right? Or rather, you need that increase in pressure from the shock to meet the boundary condition. Just a smaller increase, so it's not as strong of a shock. Okay, so the oblique shock forms at an appropriate angle to force P2, which we'll call state after the first oblique shock, state 2, to force P2 equal to P back or P receiver. Okay, so let's draw this initial shock here. Okay, so the flow's coming in this way, and we needed to pass through an oblique shock, just kind of like we did in our diagram. And the reason why I drew that center line there is because it's always going to be symmetric with respect to the center line, right? There's no reason for it not to be. So, so the picture is always going to sort of look this way, right? And then, so now this state here is still state 1, and then state 2 is here. Okay. Now the question is, which direction is the flow being deflected as it goes through this shock. Well, let's take a look at our oblique shock diagram here. In fact, this is poorly drawn because V2 looks like it's in the same direction as V1. But in reality here, because V2 perp is smaller than V perp 1, right? And we have the same V parallel as we had before, V2 always gets deflected towards the, let's say, towards the shock, towards the shock itself or away from the shock normal. V parallel is the same as V parallel as before. So same with this, you can see in this picture here, when the flow is directed upwards, the oblique shock is tilted in that way. So the flow is always directed sort of towards the shock plane, and so the second flow is kind of going something like in this direction, like that. Okay. Let me draw that a little bit better because we'll need like that, and that's not an M2. Okay, and then what this flow direction actually sort of enforces is a what you can think of as a free boundary that starts at that nozzle boundary. Because since the flow is changing direction, you can think of this dotted line that I'm drawing here as a line that the flow is never going to to cross rather. So since the flow has changed direction, that bottom dashed line forms a free boundary with the flow, and the pressure in that region P2 is equal to PB. Okay, and so that's happening on both sides. Okay, so we have M2 up here as well, and the pressure up there is the same. Okay, but now we have another problem where these two flows are going to want to interpenetrate, right? And we're dealing with not super rarefied flows. We're dealing with continuum medium, so it's not the two flows can't completely interpenetrate because it's a collisional continuum medium, and so they're going to have to meet each other, right? And then now the direction is forced at this collision point to then be parallel to the center line, right? So there's another change in direction that's going to be enforced as these two flows from either side of the center line meet each other. It needs to go like this, right? And this is going to be a new region, region 3. So this will be, we'll call this M3. And then the question is, okay, what kind of structure is going to give rise to this change in direction, right? Well, it's actually just another oblique shock. It just looks like this guy here. Maybe a little bit easier to see on the top side of the diagram here, but this oblique shock occurs to meet the flow direction boundary condition. So the first oblique shock out of the exit of the nozzle is occurring to meet the pressure boundary condition, and then the next oblique shock is occurring to meet a flow direction boundary condition with the center line. Okay, so oblique shock forms an appropriate angle to force the pressure boundary condition, and then an additional oblique shock forms to enforce a flow direction boundary condition. where that flow direction is parallel to the center line. Right? Okay, but then, well, now what's the problem? So we've gone from the pressure at N1, which was too low, right? And then we went through a oblique shock to raise it up to be the same as the receiver pressure, PB, right? And now we just went through another shock. So the pressure in region 3 is actually greater than PP because it just went through another shock. And now we're not meeting the pressure boundary condition anymore, right? So problem, P3 is larger than PB, which means that the pressure boundary condition no longer satisfied. Right, so now we need some kind of expansion. Okay, and then that is what takes us to Prandtl-Meyer flow. So, who were Prandtl and Meyer? Well, let's go ahead and look at some photos of these two gentlemen. Prandtl was a very, very famous fluid dynamicist. I believe he's actually something like the third or fourth grade grant advisor to another OSU professor, Prandtl-Meyer. I might be wrong about that, but I think that's correct. He's a very, very famous fluid mechanics theoretician and experimentalist from the early 20th century. He did most of his impactful work before World War I, and it became very important in aerodynamics. He's definitely cited as one of the fathers of aerodynamics, and was very integrated in the development of the German Air Force. And you know, he's got very famous dimensionless quantity named after him, and a huge number of phenomena. He had a very, very impactful career. Also, was fairly sympathetic to Nazi Germany, and that's you know, historically perhaps a little bit of a stain on his legacy, but nevertheless, very interesting person who had a very impactful career and impactful life. Now Meyer, we actually didn't learn too much about him until recently. He was one of Prandtl's students, and he published his thesis on oblique shocks and these expansion waves that we're right about to discuss now in 1908. And his PhD thesis probably is the most impactful PhD thesis in fluid mechanics that was ever published. But he went off to World War I, and when he returned, he wasn't really able to get work doing research. At one point, Prandtl wanted to bring him back to do some experimental work, but the work wasn't funded, and so Meyer kind of dropped out of the historical record until very recently. He was found to have spent the rest of his years as a high school math and physics teacher until his death in 1972, and nobody in his town knew that he had this huge impact on the field of fluid mechanics. And so he kind of faded into obscurity a little bit. But early in his life, I mean, I think he had even been tutored by Minkowski and Runge of Runge Kutta fame, and so, you know, his star shot high, and he made a huge impact, and then unfortunately wasn't able to continue working in the field. But he was sort of a brilliant mathematical mind paired with Prandtl, who was just this astonishingly genius level understanding and intuitive understanding of fluid mechanics that led him to be such a good experimentalist and hunt down the phenomena in a way that helped elucidate what was going on to everybody else. So interesting story from both of these guys, two Germans that helped us understand all these supersonic phenomena way back 100 years ago. So very very foundational figures. But so let's go ahead and talk about what these two gentlemen discovered. Okay, so the first thing is, remember that. Oops. Let's remind ourselves that we know what the pressure change is across a normal shock. So we know across a normal shock, the pressure changes. The static pressure changes a function of just the upstream Mach number and the ratio specific heats, which you can write as 2 gamma over gamma plus 1 times m1 squared minus gamma minus 1 over gamma plus 1. Okay, we can subtract 1 from both sides and rewrite this as P2 minus P1 over P1 is equal to 2 gamma over gamma plus 1 times the quantity m1 squared minus 1. Okay, and so the takeaway from that is simply that so let's write here, takeaway. The pressure drop across a shock is proportional to this quantity m1 squared minus 1. Okay, so keep that in mind. Let's file that away for a second. Now let's talk about the entropy change across a normal shock. So the entropy change of a perfect gas is delta S, or delta S itself, is equal to R times gamma over gamma minus 1 times the natural log of the ratio of the density upstream and downstream of the shock plus 1 over gamma minus 1 times the natural log of the ratio of the pressure downstream and upstream of the shock, which we can rewrite as R times the natural log of the quotient rho 1 over rho 2 raised to the power gamma over gamma minus 1 times P2 over P1 raised to the power 1 over gamma minus 1. Okay, just using some logarithmic rules. Now we know that those two quotients are just a function of m1 and gamma. And if we sub those relationships in and perform some algebraic manipulations, including a Taylor expansion, then we obtain the following. So in this era, we're subbing in something, the P1 over P2 being some function of m1 and gamma, and then we're doing a Taylor series expansion, algebra. So lots of steps omitted here. But what you end up with is delta S over R is equal to 2 times gamma times the quantity m1 squared minus 1 to the third power divided by 3 times gamma plus 1 squared. Let's make that clear that this is a 3 here. Plus dot dot dot, basically higher order terms, which is what I'm saying by HOT, right? And then omitting all those higher order terms is justified because we're actually more right now we're focusing on the weak shock limit. Weak shock limit. That is where M1 is approaching 1. Okay, and so what this is telling us though is that the entropy change across the normal shock is proportional to M1 squared minus 1 to the cubed, to the third power. Okay, so that's the takeaway from looking at the entropy change across the shock. All right. So now let's focus on the deflection angles. So stick with me here. We're developing this idea of these Prandtl-Meyer type flows. So it's what we're working towards here. Things that can essentially changes in direction that can occur so gradually that you don't have a change in entropy. Okay, that's the argument that we're building. So for an oblique shock, we know that m perp is equal to m sine theta, right? So therefore, we know that the change in pressure across an oblique shock is proportional to m1 squared sine squared theta minus 1. And the entropy change across an oblique shock is proportional to m1 squared sine squared theta minus 1 to the third power, right? So let's consider the case of a very weak shock. Consider a very weak shock. So essentially that means that our shock angle, theta, is approaching mu, the Mach angle, right? And importantly, the deflection is also going to 0. So the weak shock is the case where you have 0 deflection. So we know that the deflection angle satisfies, from the previous lecture, we know that the deflection angle satisfies the equation tan delta is equal to twice the cotangent of theta times the quantity m1 squared sine squared theta minus 1 divided by m1 squared times the quantity gamma plus cosine of 2 theta plus 2. Okay? And so in this limit, that is the limit that theta goes to mu, which remember that mu is equal to the inverse sine of 1 over n. So in that limit, delta is approximately equal to twice the cotangent of mu, times this overall quantity, m1 squared sine squared theta minus 1 over same as before, m1 squared times gamma plus cosine of 2 mu plus 2. And so that allows us to say that delta is proportional to m1 squared sine squared theta minus 1. Okay, and so I know this seems a little bit dubious. So, like cotangent, we have replaced the theta in the cotangent argument and also in the denominator, but we didn't replace it in the numerator. But the reason why is because cotangent mu is just equal to, the square root of m1 squared minus 1. And the denominator ends up being equal to m1 squared times gamma plus 1, which are just sort of two positive values, where m1 squared sine squared mu minus 1 in the limit is identically 0. So that term sort of dominates the limit. That's why we leave that one to be remaining to be a function of theta. At least that's the best argument I can think of for this thing. I need to go back and actually see if I can find Meyer's thesis, so I can justify this step further. But as far as the textbook goes, this is sort of the best explanation I can come up with for coming up with this argument here. So what does that mean? Okay, so we have that delta, the deflection angle, is proportional to m1 squared sine squared theta minus 1. Okay, and given the two arguments above about the pressure drop and the entropy drop, that means that we can state how both of those drops are related to the deflection angle, namely that the pressure drop is proportional to delta, but the entropy drop is proportional to delta to the third power. Okay, and this is the important fact. So now imagine that we have a gradual turn composed of n small delta deflections. Okay, so what I mean by that is we have a flow coming in on a flat surface at m1, and then we have a very, very, very small deflection, call it delta, and then we have another very, very, very small, this is actually extremely exaggerated, the deflections are much smaller than this, and then that we have that continue through a bunch of deflections until we reach our final Mach number mf. Okay, and we have a very weak oblique shock that results from each of these small deflections. This would be m2 after the first shock, and then we have m3 after the second shock, and so on until we reach this m final after the last shock. Okay, and so what you end up with is, let's make sure I'm still, yeah. So what you end up with is, for each shock that you have, you get some pressure increase, in this case, that's proportional to your deflection angle, and a change in entropy, or an increase in entropy that's proportional to the deflection angle raised to the third power. So why does this matter? Well, once we add all this up, you can say that the total change in pressure is going to be n times delta, or proportional to n times delta, which we'll just call delta total, okay? And the total change in enthalpy is going to be proportional to n times delta to the third power, okay? So now let's just take the limit as n goes to infinity. So what are we doing here? Really what we're doing is we're changing this gradual incremental change in direction. As we take the limit as n goes to infinity, we're making that change into a very, very gradual sloping change between the original direction and the other direction. Say it's like it would be like you're following the chord of a circle. Okay. So when we take that limit, we end up with limit as n goes to infinity of delta p total is equal to lim as n goes to infinity of n times the quantity delta t over n, which just equals delta t. So therefore, I should say proportionality sign here. So our total pressure change is still just proportional to delta t, but the crucial thing is that the limit as n goes to infinity of delta S total, the total entropy change, is proportional to the limit as n goes to infinity of n times delta t over n to the third power. So remember, delta t over n is just delta. And so we end up here is the limit as n goes to infinity of delta over n squared, which goes to 0. And so the total entropy change, if we go through a very smooth change in direction, is actually 0. So in the limit of a smooth turn through the deflection angle delta t, the shock waves, here I'll actually make this into a list. So in that limit of a smooth turn, we have that the shock waves approach Mach waves, which may have mentioned, I think I mentioned this in the first oblique shock lecture. But a Mach wave is the limit of the weakest possible oblique shock. So it's an oblique shock that occurs at the Mach angle. Okay, so the shock waves are approaching Mach waves. The overall Mach number is changing continuously. And there's a finite pressure change. In this case, it's an increase. And then, most importantly for this argument, the change in entropy is 0. It's an isentropic process. Okay? And so what this looks like from a diagrammatic standpoint is you have a flow coming in, flat, it goes through a smooth change to a second direction here. and you follow these two down like this, and this would be delta tot. And then for this region of changes in directions, you have all these Mach wave oblique shocks coalesce to form an oblique shock here at some angle delta, and that oblique shock is forming at the angle required to produce the total deflection angle. So the weak shocks coalesce to form oblique shock at angle theta to produce delta t. Okay. So what do we have here? How would we describe this in words? We have an infinite number, an infinite number of infinitesimal compression waves. So they decreased the Mach number, decreased m, and increased the pressure isentropically. They moved along an isentrope, and because they did it isentropically, that means that the process is reversible. Right? An isentropic process must be reversible. So because we have this isentropic mechanism for compression, that means we must have a synonymous mechanism for expansion. And what does that look like? Well, you have that. You could have the flow turning downwards like this. And so we have our initial M1 coming in like this, and then we have all these weak shocks at slightly different angles. Call this M1. And our final angle here is going to be, let's say that this is our M2. So then we call this mu2, which is actually less than mu1, strictly, because now we're expanding and therefore speeding up. So M2 is greater than M1 because we're expanding. We're going to lower pressure, and then that's why M2 the Mach angle is going to be smaller, right? This can also occur around a corner, a sharp corner, with what would be called a centered expansion fan. So you can have your incoming Mach angle, or sorry, Mach number there. You have your exiting Mach number M2, which is larger than Mach 1, and then you have all these expansions here that occur like that, and the final expansion fan angle would be m2 less than m1, and then the first expansion angle is measured relative to the first flow direction, m1. Okay? So these are called Prandtl-Meyer expansions. Prandtl-Meyer expansions. Oops. Before the previous things were PM compressions, or Prandtl-Meyer compressions. All right. So that's the general idea here. So remember, just to recall here, why did we go into this? Well, we had this nozzle structure where we knew that after a few changes in direction, we were going to have a pressure that was too high to meet the pressure boundary condition, and we needed some sort of mechanism that allowed the flow to expand to meet the pressure boundary condition again. And the way that we do that was we needed some sort of expansion mechanism, and so we went and learned about how Meyer and Prandtl worked out an expansion mechanism by constructing an isentropic compression process that must then be reversible, and then we can use that principle to define an expansion process called the Prandtl-Meyer expansion. Okay, so let's do some further. Excuse me. Let's do some further analysis of these Prandtl-Meyer expansions. So let's consider an infinitesimal Prandtl-Meyer expansion. So we have some flow coming in, change in direction that way. We'll say that the deflection angle here is some d delta, so a very small deflection angle. And then we have this expansion wave, which will be at the angle theta min, the minimum shock angle, which is equal to mu. And then we have a resultant flow that is the original flow m, or original flow Mach number m plus some increment in Mach number, and then of course we have the incoming flow at a Mach number of m. Okay, so it's the same thing as an oblique shock. Only the perpendicular component of the velocity is changing. What do I mean by that? Well, we have some sort of parallel velocity, v parallel, right? And the original of velocity is moving along in that direction at an angle mu, at the Mach angle, and then the next flow is sort of separated by the original flow by a d delta, very small deflection angle, and the magnitude of that vector is v plus dv. Okay, so only perpendicular components of v changes, same as for oblique shock. And we can use that fact to do some algebra. So the parallel component of the velocity is equal to v times the cosine of mu. Okay, just by the virtue of that diagram that I just drew. And we know that that's going to be equal on the other side to v plus dv times the cosine of mu plus d delta, right? And if we expand this out using trigonometric identity first, we get cosine of mu times cosine of d delta minus sine of mu times sine of d delta. Okay, and we're talking about the limit where delta is very small. The cosine of an angle very, very close to 0 is essentially equal to 1, right? And the sine of an angle that's very, very close to 0 is approximately 0, because it's not 0, rather. It approaches just the small angle itself, so d delta. And this is a 1 here. And so now we can use those two facts and then write out the full sort of FOIL out the binomial expansion here, where we have v times the cosine of mu minus d delta v times the sine of mu. I'm going to put the d delta at the back. So v sine mu d delta plus cosine of mu dv minus sine of mu dv d delta. And for reasons that we said before, this term is going to go to 0, or at least it's small compared to the other terms, because those two infinitesimals multiplied by each other, while the rest of the terms have 1 or less. And then v cosine mu actually is appearing on both sides here, so we can cross that out as well. And so what this tells us is that we can express the infinitesimal deflection angle as cotangent mu times dv over v, which, as we stated before, cotangent of mu is equal to the square root of m squared minus 1 times dv over v. That cotangent of mu being equal to m squared minus 1 has to do with the definition of mu being the inverse sine of 1 over m. So if you draw that triangle and use the definition of the cotangent, that is cosine over sine, then you'll see how you end up with that identity there. So let's label this as a star, okay? And then we're going to assume a perfect gas. Where v is equal to n times the square root of gamma RT. Okay? And in that case, dV is equal to the square root of gamma RT times dm plus n times the square root of gamma r over 2 root t dt. So taking the total differential of that v equals m times the square root of gamma RT. And then we divide both sides by our identity directly above. We end up with this dv over v equals dm over m plus dt over 2t. And let's label this guy with a dagger. Okay? So we have the star relation, we have the dagger. Let's hunt for a couple more, okay? So first, let's recall the stagnation temperature, where we have the stagnation temperature being equal to T times 1 plus gamma minus 1 over 2 m squared. Okay, we can take the total differential of that guy, T, the D stagnation temp is equal to the quantity 1 plus gamma minus 1 over 2 m squared times dt plus the quantity gamma minus 1 T m dm. Okay. But we know that we don't have no heat or work being done, right? Q or WS. So if we have no heat or work being done, that means that our stagnation temperature, because we're dealing with a perfect gas here, is constant, right? So dTT is equal to 0, and these two things allow us to write that dt over t is equal to minus gamma minus 1 m over 1 plus gamma minus 1 over 2 m squared dm. Okay, so now let's sub into dagger. So we take that result, we put it in dagger, and we get dv over v is equal to dm over m minus gamma minus 1 m over 2 plus gamma minus 1 m squared dm, which results in the quantity 2 over m times the quantity 2 plus quantity gamma minus 1 m squared close parentheses dm. Okay, then we sub that dv over v into star, and what we get is d delta is equal to the square root of m squared minus 1 divided by 1 plus gamma minus 1 over 2 m squared dm over m. Okay? And that tells us that the infinitesimal change in the deflection angle or the flow direction is itself a function of m and gamma only. So if we integrate this, so we want to integrate this to yield an equation that is something like delta plus some integrating constant is equal to some function of m and gamma. So we integrate this to yield delta plus constant is equal to that, and we set the deflection angle equal to 0 at m equals 1, we get the following. And believe me, this is actually very important. Okay, so you get this eta pm, which we'll call nu. Okay, That's what it'll be. You'll see the way you'll see it in the tables, which is equal to this big function here, gamma plus 1 over gamma minus 1. That whole quantity multiplied by the inverse tangent of gamma minus 1 over gamma plus 1 times m squared minus 1 minus the square root of the inverse tangent or the arctangent of m squared minus 1. Okay? So that's after doing that integral. And this is called the Prandtl-Meyer function. So what the heck does this thing describe? The key is sort of the boundary condition that we chose, right? So what did we solve for here first of all? We started with an infinitesimal deflection angle or Prandtl-Meyer expansion, okay? And then we integrated that over many different infinitesimal changes in direction so that we can relate a total deflection angle to an upstream Mach number, right? So this is delta PM is the angle measured from the flow direction where m naught equals 1, through which the flow has been turned isentropically to reach m. So is the angle measured from m naught equals 1 through which the flow has been turned isentropically to reach a Mach number of m. Okay? And then this is new in Appendix G of the textbook. Okay, it's tabulated for m. So hopefully I'm going to show you a couple of examples, and hopefully that definition will make sense in just a moment. So let's look at the first example. So in the first example, let's start with m1 equal 1 so that it sort of matches the definition. So in the first example we have m1 equals 1, okay, and then we have a deflection angle, 28 degrees, okay, and then the question that we would be asking is, after we change the flow through a isentropic expansion through 28 degrees, what would m2 be? Okay, and so we have this function here. It's tabulated for values of m, and so you would go to the table. You would look up nu is equal to 28 degrees, since you know that m1 was 1, and that would tell you that m2 must be equal to 2.06 via the table. Okay, let's look at this next example. This is a little bit more complicated. So in this case, we have our first m1 being equal to 2.06. What we just got, okay? And then we're going to turn it through an additional 12 degrees. And then we want to know what M2 is, right? So what you do here is you need to imagine that your initial Mach number was obtained through a previous Prandtl-Meyer expansion. Okay, so if M1 is greater than 1, imagine that was obtained via a previous Prandtl-Meyer expansion. So what do I mean by that? Well, I want you to go in here and I want you to draw a previous Mach number that led into this that started at m naught equal 1. Okay? And then I want you to find what this angle is. So let's call it nu 1. What was that? So if you go to the table and you look for M2, the Mach number after the turn equal to 2.06, because we just did an example and we know it's going to be 28 degrees. So here we would see from the table that nu 1 is equal to 28 degrees from table. And then we add the two angles together, and that would be the total. So take nu 1, 2, 1-2 is equal to nu 1 plus nu 2, which would be 40 degrees. And then you know that you're turning through an additional, or a total of 40 degrees starting from Mach number equal to 1 to get to M2, which you know is going to give you, from the tables, N2 is equal to 2.54 in this case. Okay, so because these processes are isentropic, you can do 28 degrees of rotation of the flow, and followed by 12 degrees of rotation of the flow, and that's the exact same thing as doing the entire 40 degrees to begin with. Okay, so I'll write that down. So the processes are isentropic. Which means, so the end state is the same. No matter the path or like how many steps you took in your rotation, right? Okay, so that's how you would deal with that if you had an initial Mach number that was greater than 1. Okay, so now let's do an example with a compression. So you've seen sort of the full gamut of the Prandtl-Meyer type of problems you'll probably see. So example 3 is a compression. And then that'll be the last thing that we talk about in today's lecture. So we have gradual change in direction. Whoops. Let's draw that a little bit more nicely. Okay, and like I said, we have this sort of set of compressions that coalesce into a shock. Let's say we have M1 is equal to 2.4. We have that the initial static pressure is 325 Kelvin, and the initial static pressure is 1.5 bar. Okay? And then the question becomes, what are the downstream conditions? What's M2, what's P2, and what's T2? But we know that we're turning through a direction of minus 20 degrees, okay? So you have to use a negative for compression. Okay, so the first step, since we're starting with an M1 that's greater than 1, is we know that from the tables we'll find that M naught, or sorry, V new we'll call this new 2. So that we know we'll find that new 1 starting from over here, right? New 1. New 1 was 36.75 degrees, and we got that from knowing what M1 is. Then we'll get new 2 being equal to or rather, we'll get we'll get M2. So then we'll get new 1-2 is equal to 16.75. Okay, so we just subtracted 20, which tells us that M2 is equal to 1.664. Okay, and then also, crucially, this entire process is isentropic, so PT1 is equal to PT2, and TT1 is equal to TT2. So we know that P2 is equal to P2 over PT2, PT2 over PT1, PT1 over P1. So this is just a function of M2. This is just a function of M1, and then this is equal to 1. And what you end up with in that case is 4.7 bar for P2, and then T2 has much the same reasoning and ends up being 450 Kelvin. Okay, hopefully that makes sense. But the key insight here is that because the way that we did this integration, we said that the deflection is equal to 0 at m equals 1. So when we look at this tabulated function, if we have an initial Mach number that's greater than 1, we have to figure out what the turn would have been starting from 1. And then we add and subtract the angles appropriately to obtain the downstream conditions after the required direction change that we're looking for. Okay, you'll get some help and practice working with these ideas in your homework. Next time so remember, the whole thing that motivated us to go down this path was because we kind of had reached a dead end in our analysis of what was going on outside the nozzle in between the second and third critical. Now we're going to be able to bridge that gap because we have these Prandtl-Meyer flow structures to work with. So that's basically where we're going to start next lecture. And then once we're done with that, we'll go back to some external flows, this time with friction, and talk about fan no flow. So hopefully you'll stick around for that. Have a great remainder of your day. Hope to see you next time, and take care.